All right, hello, ladies and gentlemen. This is Mrs. Masteller, and we are continuing on with a new chapter, which is technically going to actually be chapter 11 out of your textbook, but these first few sections will actually be from chapter 0 of your textbook, meaning this is probably stuff that you should already know. These first few, though, honestly, this first section in particular, counting techniques, I know this is definitely something you've never seen before. But we're going to be doing probability is kind of the gist of this chapter, a lot of probability, stats, things of that nature. Okay, so starting with the fundamental counting principle at the top. So here's what the fundamental counting principle is, and that's what we're obviously going to be using here for these first few examples. Okay, so here's what the fundamental counting principle says. It says if event M can occur in M ways and is followed by event N that occurs in N ways, then the event M followed by event N can occur in M times N ways. Really, the gist of it when it comes to the fundamental counting principle, you're really just multiplying out the number of choices that you have. Okay, so you'll kind of see how it all unfolds and plays in together as we go through these examples, but it says that we also use permutations, combinations, and other counting methods to determine the number of ways that events can occur and to calculate the probabilities, including the probability of compound events. Okay, so we'll be getting to that again a little bit later on. But talking about being independent versus dependent, so an independent event is just when you have one event that's not affected by another one. So one event is not, I'll put the emphasis on that, affected by another event. So they basically just kind of stand alone. Okay, or you can think about it too as your choices. So one choice is not going to be affected by another one. And these are some all examples of independent events, independent choices that we can make. So example one, you're at a sandwich cart and it offers customers a choice of hamburger, chicken, or fish on either a plain or sesame bun. So we want to know how many different combinations of meat and bun are possible to make a sandwich. Okay, so how many different sandwiches can we create? Well, we have three choices for the meat, hamburger, chicken, or fish, and then we could do a plain or sesame bun. So we have two choices for the bun. So we have three choices for the meat, two choices for the bun. Looks like you can make a total of 6 different combinations of a bun with a sandwich. So again, this is an independent event because, you know, the meat that I choose is not affected by the bun that I choose, and same thing vice versa. I make these choices independently, so on and so forth. Okay? We also might see it kind of like this. This is called a tree diagram. So again, I can do hamburger, chicken, or fish, right? There's my choices, and I could do hamburger on a plain or hamburger on a sesame. I can do chicken on a plain, chicken on a sesame, fish on a plain, or fish on a sesame. So again, if you count this out, hamburger plain, hamburger sesame, again, that's two different choices, chicken plain, chicken sesame, fish plain, fish sesame. So you can even actually see all different 6 combinations that you can create. Okay, so you can always just make a tree diagram, which is probably the more so elementary way that you guys probably remember going through and finding out all the different combinations that you can make. Okay? So we're just using the fundamental counting principle again. You're really just multiplying out the number of choices that you have. So as an example, here's another one. And again, this is an independent event. It says to make a yogurt parfait at Dairy Queen, you can choose a flavor of yogurt, one topping, and then one nut topping. So how many parfait choices are there? Well, as far as the flavor of yogurt goes, the flavors, we could do plain or vanilla. I honestly don't really know what the difference is, but you have 2 choices here, right? And then as far as the fruit topping, we can do 1, 2, 3, 4, 5 choices. And then we could do almonds, peanuts, or walnuts. That's 3 choices. So again, you could diagram this out, which would actually be a pretty large diagram once it's all said and done, especially because you have 5 different fruit toppings to choose from. But realistically, to figure out how many different parfait choices you have, You're simply multiplying all your choices together. So 2 times 5 times 3, there'll be 30 different parfaits that you can create. Okay? Number 3, it says many answering machines allow owners to call home and get their messages by entering a 3-digit code. So how many codes are possible? So I'm creating this code for my home answering machine. It's kind of an old school thing. But to access my messages, I have to enter in this 3-digit code. Okay, so it's 3 numbers long. Right? So just think about what choices do we have? What choices do we have for that first value? So even thinking about, when you have your lock screen on your phone, think about the numbers that you can choose from for that first digit. You have the numbers basically 1 through 9 plus 0. So that's 10 total choices you have for that first digit. And then you would still have 10 choices for the next one, and then 10 choices for the last one. Okay, because it doesn't say that you can't repeat numbers, so I can put my passcode if I want to be 000, or I can do 999, or I could do 976, or I could do 123. These are all the different choices that we have. But how many different passcodes would there be then? There'd be 1,000 different passcodes. Okay. The last one on this page, it says a password for a site consists of 4 digits and is followed by 2 letters. The letters A and Z are not used, and each digit or letter may be used more than once. So how many unique passwords are possible? So again, it's going to be 4 numbers. So here's kind of my setup. It's going to be 4 numbers followed by 2 letters. So I usually just put alpha and alpha. Just know I'm choosing a letter out of the alphabet. Okay, and again, it does say the letters A and Z are not going to be used, and each digit or letter may be used more than once. So pretty similar ideas above. Again, you have 10 choices for each number. And as far as the letters go, well, you have to know how many letters are in the alphabet. So from A down to Z, there's 26 letters in the alphabet. But we can't use A or Z, it says. The letters A and Z are not going to be used. So for each letter, we now have 24 choices for each of these. And this is what you'd be multiplying. Okay, so again, you're just multiplying out the number of choices that you have for each event. So when you multiply this all together, you should get 5,760,000 different passwords. And there you go. All right. Now on to the next page. Now we're moving on to dependent events. So dependent is when your one outcome or one event is going to be affected by another one. So this time one event is affected by another event. So each choice I make is going to be affected basically by my previous choice. Okay, so I don't have standalone choices in this case. So it says that Sarah must take, so here's an example, Sarah's going to take 6 different classes next school year, assuming that each class is offered each period, how many different schedules could she have? So again, she's creating her own schedule, right? So a lot of you are probably going through this right now. She takes 6 classes though at her school. So let's just say as an example, she's going to take a math class next year. She's going to take an English class. We'll just say history, social studies of some sort, probably a science class, maybe PE, and then maybe an art class. Okay, there's the 6 classes she's taking. So she could put these in any order that she wants to. So pretend like you're the guidance counselor and you're trying to arrange her schedule around. Let's say she puts math first period, right? So when she chooses that first hour class, she has all 6 choices to choose from. But once she puts math to be first period, she can't have math again. So again, my next choice is going to be affected by my previous choice. So now I'm down to 5 choices, and then I'm down to 4 choices, and then 3 choices, and then 2, all the way down to where we only have 1 left. Okay, so again, if I choose math first hour, I can't choose a second hour, so that I'm down 1. So maybe I put science second hour, so now I'm down to 4 choices, again, so on and so forth. Okay, so if you multiply this all together, there'll be 720 different schedules that she can create. Okay, a password is 4 letters followed by 1 digit, so how many passwords are possible? And here's the key words: no repetition is allowed. You cannot repeat. So again, let's see, it's 4 letters. So here's how I'll kind of set it up. Alpha, Alpha, that's 4, and then one number at the end. But you cannot repeat. So when you choose that first letter, you have all 26 letters in the alphabet to choose from. But let's say I choose the first letter to be M. Well, then the next one can't be an M because I can't repeat my letters. So now I'm down to 25 choices, and then I'm down to 24 choices, and then 23. But as far as the numbers go, I mean, I have all 10 choices for the number, for the digit. Okay, so this is what you'd be multiplying. So when you multiply that all out, you should get 3,558,000 different passwords. All right. So what we basically just did, for at least the first one for sure, is we did this thing called a factorial. Okay, so if you have n factorial, what is n factorial? It's basically taking that number, whatever that number is. So that's how you read that exclamation point too. It's called a factorial. So n factorial is basically n times n minus 1 times n minus 2 times n minus 3, all the way down to when you're multiplying times 1. Okay, so you're basically going to keep multiplying by the previous digit all the way down to until you get to 1. So as an example, what is 6 factorial? We basically just did an example 5, but 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1, which again we saw to be 720. Okay, so we're just going to practice working with some factorials. So 12 factorial as an example. So that's doing again 12 times 11 times 10 times 9, 8, 7, 6, 5, 4, 3, 2, all the way down to 1. So 12 factorial should come out to 479, looks like million, and then 1,600 is what you should get. That is 12 factorial. The next one, we're doing 3 factorial, basically times 5 factorial. So 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. So multiplying this all together, you should get 720. Okay, for C, so there's kind of a little trick to this. So we have 6 factorial over 2 factorial times 4. So I'm just going to write it all out. So here's 6 factorial on top. On the bottom, we have 2, and then also 4 factorial. So a lot of this, you don't even have to really multiply a lot of it. You can honestly do some canceling that'll help you with your multiplication. So for example, like the 4, the 3, the 2, the 1, those all cancel down. So now all I'm really left with is 6 times 5 over 2 times 1. I can cancel down a little bit more if I'd like to, like 6 over 2, because that's just 3 over 1, making my ultimate answer just 15 over 1, or just plain old 15. So you can always do some canceling as you go. So like even for the next one too, for D, right? I know I have 8 factorial on top, which is 8 times 7 times 6, but I'm going to stop there because I know if I keep listing out 5 all the way down to 1, that's just going to cancel with the 5 factorial. So on the bottom, I'm really just going to list out 3 factorial. Because again, from 5 on, that just cancels with the 5 factorial. So now, if I go ahead and reduce this down a little bit, let's see, I'm going to do the 3 with the 6. So divide those both by 3, and then 2 over 2 obviously just cancels. All we have left is 8 times 7, and that's 56 over 1. All right, so why do we have to know factorials? Well, that's where these come into play. So we have these things called permutations. It's when you're selecting a group of objects in which the order does matter. So these are more so like dependent events. So I'm just going to put a capital D next to it. The order in which I choose these things does matter. And here is kind of the special formula we're going to be using. Okay, so I'll go through and explain everything. And there's an example for you too. All right. But key words to know the difference between, because this is the hardest part of the lesson, is knowing when is it a permutation, when is it a combination. So a permutation, these are kind of the key things I want you to think about. If a problem is talking about position of office, so if you want to put position, I'm going to say of office. So if it's talking about, you know, choosing a president, a vice president, a secretary, a manager, an assistant manager, that's a position. Okay, so that's automatically going to be a permutation. If they talk about placing, like in a competition, So if they're talking about, you know, first place, second place, third place, the gold medal, the silver medal, the bronze medal, if I'm placing a competition, the order in which I choose those, again, is going to matter. My next choice will be affected by my previous one. If it talks about arranging items or rearranging items, that's going to be a permutation. If it talks about putting things in order, again, that's also going to be a permutation. Okay, so these are all just things to look out for when you're reading through and trying to decipher between is it a permutation, is it a combination. Okay, so again, here's an example down here. So it says the number of permutation of 7 items taken 3 at a time is represented by, okay, so this is basically the total number that you have, and here's how many you're taking from there. So I have 7 total items, I'm taking 3 at a time. So this would be all plugged into the formula. So n should always be the bigger number, okay, when it comes down to it. N should be the bigger of the two numbers if there's a choice, and then r is going to be the smaller one. Then you just simply plug it into the formula. So n factorial goes on top, and then n minus r factorial goes on the bottom. So here's some examples. Okay, so it says 8p7, right? So that means I have 8 total items, and I'm choosing 7 of them. So that's going to be 8 factorial over 8 minus 7 factorial. So that'd be 8 factorial over, that would just be 1 factorial on the bottom. So 1 factorial, obviously it's just 1, so we're really just doing 8 factorial. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,320. Okay, so 5p5, if I have 5 total items, I'm taking 5 of them at a time. This is going to be equal to 5 factorial over 5 minus 5 factorial. So 5 factorial over 0 factorial. And believe it or not, 0 factorial is actually 1. So just like anything to the 0 power is 1, 0 factorial is 1. So we just really have 5 factorial over 1. So that just comes out to be 120. That's my final answer. Okay, so here are some examples, like I said, of permutation. So for number 7, it says there's 10 finalists in a figure skating competition. How many ways can the gold, silver, and bronze medals be awarded? So again, it's talking about placing in a competition. So it's automatically going to be a permutation. So there's 10 total finalists, right? And we're choosing 3 of them, the gold, the silver, and the bronze medalists. Okay, so when you plug this in, what we're doing is 10 factorial over 10 minus 3 factorial. So that'd be 10 factorial over 7 factorial. So as I list this out, again, this is really all I have to do. It's 10 times 9 times 8, because I know from 7 and on, it's just going to keep on canceling. So this is all I really have to multiply, 10 times 9 times 8. So there's 720 ways to award the gold, the silver, and the bronze medalists. Okay? If you think about that too, it's pretty similar to the fundamental counting principle when you look at it. Because again, if I'm thinking about, so how many people do I have to choose for the gold medal? Well, there's 10 total people, so I have all 10 choices. But once I choose that person as the gold medalist, they can't win the silver too. So now I have 9 people to choose for the silver medal, and then same thing for choosing the bronze. Now I'm down to 8 people to choose from. Okay, so it's pretty much a similar idea as the fundamental counting principle. Okay, so for the next one, 8 people enter the best pie contest. How many ways can the blue, red, and green ribbons be awarded? So once again, we're talking about placing a competition. There's 8 total people, and we're choosing the top 3 basically. So that's 8 factorial over 8 minus 3 factorial. So 8 factorial over 5 factorial again. 8 times 7 times 6. I'm going to stop there because I know from 5 and on it's just going to cancel with 5 factorial. So if I just multiply 8 times 7 times 6, it should come out to be 336. That's my final answer. All right, on to combinations now. So that's a permutation where the order does matter. But if you have a combination, the way that you select these objects, the order does not matter. So that's what goes in these blanks. Order does not matter in which you choose them. So new formula. All right, pretty similar to the last one. The only difference is that you also have r factorial on the bottom. Okay, so n items taken r at a time. So again, here's an example of a combination. So the number of combinations of 8 items taken 5 at a time is represented by, so 8 total items. Again, bigger number is n, smaller number would be r. Okay. So when you plug this into their formula, so if it's 7, choose 1, we would have 7 factorial over 1 factorial, and then 7 minus 1 factorial. So this would be 7 factorial over 1 factorial, 6 factorial. So it really just ended up being 7 in the very end. So if I have 7 total items, right, and I'm just choosing one of them, how many different ways can I do that? There's 7 different ways to choose one item if there's 7 of them. Okay, so it kind of makes sense too when you think about it with the combination. So the next one, so 2 choose 2. So n and r, right? So to have 2 factorial, and then 2 minus 2 factorial plugged in. So 2 factorial, 0 factorial, which again, I told you guys that 0 factorial is really just 1. So we're really just doing 2 factorial and 2 factorial is really what we're getting at. And then this answer would just obviously end up being 1 in the end. So if you have 2 total items and you choose both of them, how many different ways can you do that? There's only one way. Okay, you're not choosing one and then choosing the other one. You're basically grabbing them at the same time. So there's only going to be one way to do that. If I have 2 total items in front of me, how many different ways can I choose those 2? There's only one way to do it. Okay? So for 11, this is an example of a combination. So it says a group of 7 students working on a project needs to choose 2 from their group to present their group's report to the class. How many ways can they choose the 2 students? So again, 7 people are working on the project, and 2 of them have to go present the project. Okay, they're not saying the top 2 students in the group. They're not saying, you know, the 2 best performing students or anything like that. If that were the case, then it would be a permutation. But we're just saying that 2 students out of this group of the 7 have to go present. So that makes it into a combination. So plugging this all in, you'd have 7 factorial, 2 factorial, 7 minus 2 factorial. So 7 factorial, 2 factorial, 5 factorial. So I'm just going to list out again 7 times 6 and then 2 times 1 because from 5 on it's just going to cancel anyways. So 6 over 2, I can reduce that down to be 3 over 1. So my answer would just be there's 21 different ways to choose 2 students of the 7. Be my final answer. Okay? Next one, 5 cousins at a family reunion decide that 3 of them will go pick up a pizza. So how many ways can they choose the 3 people to go? So again, there's 5 total. We need 3 people. Again, it's a combination because it doesn't matter which 3 go. Any of the 3 can go. We're not saying the 3 favorite cousins or anything along that line. So it's going to be a combination. Okay, so plugging this all in. 5 factorial, 3 factorial, and then we got 5 minus 3 factorial. So 5 factorial, 3 factorial, 2 factorial. So I'm going to list out 5 times 4, because again, I know from 3 on it's just going to cancel with 3 factorial. So I'm just going to list out the smaller one, which is 2 factorial, reducing this down a little bit. So there's 10 different ways that we can choose 3 cousins to go out of the 5 to go pick up the pizza. All right, Kelly chooses 3 of the 15 flavors of ice cream at the grocery store, so find the number of possibilities. So there's 15 total choices, and again, she wants 3 of them. Doesn't matter which 3, doesn't have to be her 3 favorite flavors, just any 3 flavors. She's just going to snag them and then continue on her way. So this would be 15 factorial, 3 factorial, 15 minus 3 factorial. So 15 factorial, 3 factorial, 12 factorial. So 15, 14, 13, I'll stop there. Again, I know from 12 on it's just going to cancel with 12. So now I'm just going to list out the 3. So reducing this down, that's 5 over 1. That'd be 7 over 1. So the bottom is all just 1 now. So it's just 5 times 7 times 13. And you should get 455 different ways. All right, well, there you guys go. There's the fundamental counting principle, permutations, combinations. All right, hopefully you found this lesson to be useful. Let us know if you have any questions. Otherwise, have a great day.